In order to enter coordinates in a GIS, we need to uniquely define the location of all points on Earth. We must develop a reference frame for our coordinate system and locate key positions on this system. Since the Earth is a curved surface and we work with flat maps, we must somehow reconcile these two views of the world. We define positions on the globe via geodesy and surveying. Geodesy is the science of measuring the shape of the Earth and locations on or in the Earth. Once we define these positions, we convert these positions to flat surfaces via map projections. Because of three factors, we will encounter several different sets of coordinates to define the same location on the surface of the Earth. Let's review these three. A flat map must distort geometry. Because we plot latitude and longitude coordinates on a flat map, we must use a map projection to reconcile the portrayal of the Earth's curved surface onto a flat surface. The second main problem in defining a coordinate system is the irregular shape of the Earth. We learn early on that the Earth is shaped as a sphere. This is an approximation because past and present natural forces yield an irregularly shaped Earth. These deformations affect how to map the surface of the Earth in a Cartesian coordinate system used by a GIS. Thirdly, our measurements are rarely perfect. All locations depend on measurements that contain some error. Our measurements improve through time, and this evolution means our estimates of positions change through time. As an example, this slide shows a U.S. benchmark, which is a precisely surveyed and monumented point. Coordinates for this point are maintained by federal and state government surveyors, and resulting coordinates are shown at the top right of the figure. Note that there are three different versions of the latitude-longitude location for this point. In this case, the three versions differ primarily to differences in the measurements used to establish the point's location and how measurement errors were adjusted. And that was the third factor discussed above. It is crucial to realize that different ways of addressing the Earth's curvature, the Earth's deviation from our idealized shape, and inevitable inaccuracies in measurement will result in different coordinate systems. Here again we see the different modifiers for different CRS or coordinate reference systems and the resulting different values. We begin by modeling the Earth's shape as an ellipsoid. An ellipsoid differs from the geoid, a gravitationally defined Earth surface, and these differences cause some early confusion in the adoption of standard global ellipsoids. There's a long history of ellipsoidal measurement, and we have arrived at our best estimates of global and regional ellipsoids after collecting large, painstakingly developed sets of precise surface and astronomical measurements. These measurements are combined into datums. These datums are used to specify the coordinate locations of points on the surface of the Earth. A datum is a reference surface. Both horizontal and vertical datums exist. Datums are defined by an ellipsoid model of the Earth, including how the model ties into the Earth's datums changes through time as our measurements and models improve. So every latitude and longitude has a time stamp. The true shape of the Earth varies slightly from the mathematically smooth surface of an ellipsoid. Differences in the density of the Earth cause variation in the strength of the gravitational pull, in turn causing regions to dip or bulge above or below a reference ellipsoid. We can see that in the top right of this slide. This undulating shape is called a geoid. The geoid is a measured and interpolated surface and not a mathematically defined surface. Because we have two reference surfaces, a geoid and an ellipsoid, we also have two bases from which to measure height. Elevation is typically defined as the distance above a geoid. This elevation above a geoid is called the orthometric height, and you see that on the right side of this figure. Heights above the ellipsoid are often referred to as the ellipsoidal height, and you see that on the left side of this figure. Here we see two ellipsoids with the same size but different orientations and origins. One is optimized to match the geoid at one point, and the other optimized to match the geoid across a different region. Before the satellite and computer revolution, datums were typically national and continental, and they were rarely recalculated. Their origin was at the geometric center of the Earth, and it assumed a static network of points. After the satellite and computer revolution, datums were generally global and recalculated often. The origin was at the center of mass, and we could incorporate dynamic networks of points. In other words, we could measure how points were changing, a velocity, if you will, over time. Plates are moving, tectonic plates are moving, so the latitude and longitude of any point changes with time. A datum is a set of coordinate locations specifying horizontal positions for a horizontal datum or vertical positions for a vertical datum on the Earth's surface. A datum is a set of accurately determined points and associated measures and mathematical surfaces. In other words, a datum is a reference or starting point against which we measure other locations. Through various surveying, satellite, and astronomical methods, we establish a set of points on Earth for which the horizontal and vertical positions have been accurately determined. A geodic datum is a reference surface. A geodic datum consists of two major components. The first component is an ellipsoid with a spherical or three-dimensional Cartesian coordinate system and an origin. A useful datum must include a set of points and lines that have been painstakingly surveyed and that may be used as the starting points for subsequent detailed local surveys. Precisely surveyed points are commonly known as benchmarks. Benchmarks usually consist of a brass disc embedded in rock or concrete. Different datums are specified through time because our realizations or estimates of the datum change through time. New points are added and survey methods improve. There are two main eras of datums: those created before satellite geodesy and those after. Satellite positioning technologies became commonplace in the last decade of the 20th century, and they substantially increase the number and accuracy of datum points. Datums and coordinates found today are a mix of those developed under pre-satellite datums and those referenced to post-satellite datums. So the GIS user should be familiar with both. With a sufficiently large set of reference points, the survey measurements must be reconciled into a consistent set of coordinates. Small inconsistencies are inevitable in any large set of measurements. Datum adjustment reconciles errors across the network. Periodic datum adjustments result in series of regional or global reference datum. Each datum is succeeded by an improved, more accurate datum. To see how a new datum will affect analysis, consider the figure in the lower center of the slide. It illustrates how ellipsoids might change over time, even for the same survey region. Ellipsoid A is estimated with the datum coordinates for point 1 and point 2, with the shown corresponding coordinate axes, origin, and orientation. Ellipsoid B is subsequently fit after points 3 through 7 have been collected. This newer ellipsoid has a different origin and orientation for its axis, causing the coordinates for point 1 and point 2 to change. Some commonly used datums are the North American datum of 1927, NAD 27. NAD 27 is a legacy datum. Another datum is the North American datum of 1983, or NAD 83, and it's a successor to the NAD 27 datum. The World Geodetic System of 1984, WGS 84, is another set of datums developed and primarily used by the U.S. Department of Defense. A third set of datums, commonly used worldwide and increasingly in North America, is the International Terrestrial Reference Frames, or ITRF, with datum realizations from the International Terrestrial Reference System, ITRS. The conversion of the datum is important. The versions are all likewise extremely important to keep track of. NAD 83 1996 is a different realization than NAD 83 2011. The datum is incompletely specified unless the version is given. So just saying NAD 83 for the datum means you have incompletely specified it. You need to say NAD 83 1996 or NAD 83 2011. Again, a horizontal datum is a reference surface against which other horizontal distances are measured. A vertical datum is a reference surface against which other vertical heights are measured. Converting geographic coordinates from one datum to another typically requires a datum transformation. A datum transformation is a method or set of equations that allows the calculation of a point in one datum based on coordinates expressed in a different datum. For example, we can calculate the latitude and longitude of a benchmark in NAD 83 2011 when we know these geographic coordinates in NAD 83 1986. Simple formulas often do not exist for transformations involving many of the older datums. For example, from NAD 27 to NAD 83, you will not find simple formulas. Specified data transformations may be provided and they're usually provided by government agencies. Transformation among newer datums may use more general mathematical transformations between three-dimensional Cartesian coordinate systems, as we see in this slide on the figure on the left. Map projections are a systematic rendering of points from the Earth's curved surface onto a flat map. While there are many purely mathematical or purely empirical map projections, the most common map projections used in GIS are based on developable surfaces. Cones, cylinders, and planes are the most common developable surfaces. A map projection is constructed by passing rays from a projection center through both the Earth's surface and the developable surface. Points on the Earth are projected along the rays and onto the developable surface. This surface is then mathematically unrolled to form a point. A datum tells us the longitudes and latitudes of features of an ellipsoid. These points must be transferred from a curved ellipsoid onto a flat map. A map projection is the systematic rendering of locations from the Earth's curved surface, represented by a datum, onto a flat map surface. A projection converts between geographic latitude and longitude and projected x and y coordinates. The slide shows one simple projection method between geographic, in other words datum, and Mercator, in other words map, coordinates. These calculations would be applied for every point, vertex, node, or grid cell in a data set. Converting the data feature by feature from geographic, what we find in our datum, to Mercator, what we want on our map as coordinates. Most map projections may be viewed as sending rays of light from a projection source through the ellipsoid and onto a map surface. In some projections, the source is not a single point. However, the basic process involves the systematic transfer of points from the curved ellipsoidal surface to a flat map surface. Distortion will happen in this projection process. Distortion is usually small near the points or lines of intersection between the flat map and the ellipsoidal. Distortion increases with increasing distance from those points or lines of intersection. Most map projections are based on a developable surface. That's a geometric shape onto which the Earth surface is projected. Cones, cylinders, and planes are the most common developable surfaces. A plane is already flat, and cones and cylinders may be mathematically cut and unrolled to develop a flat surface. Projections may be characterized according to the shape of the developable surface as conic from a cone, cylindrical from a cylinder, and azimuthal from a plane. The orientation of the developable surface may also change among projections. For example, the axis of a cylinder may coincide with the poles of the Earth, an equatorial, or the axis may pass through the equator, a transverse. Here we see a cone unwrapped onto a flat plane and a cylinder likewise. The Lambert conformal conic and the transverse Mercator are the most popular projection types used for spatial data in North America. Standard sets of projections are commonly used for spatial data in a GIS. In the United States, the UTM and state plane coordinate systems define a standard set of map projections that are widely used. Other map projections are commonly used for continental or global maps and for smaller maps in other regions of the world. The state plane coordinate system is a standard set of projections for the United States. It specifies positions in Cartesian coordinate systems for each state. Each state has one or more zones. Multiple state plane zones are used to limit distortion errors due to map projections. One state plane projection zone may suffice for small states. Larger states commonly require several zones, each with a different projection. The state plane coordinate system is based on two types of map projections: the Lambert conformal conic and the transverse Mercator projections. Because distortion in a transverse Mercator increases with the distance from a central meridian, this projection is most often used with states or zones that have a long north-south axis, for example, New Hampshire or Illinois. Conversely, a Lambert conformal conic projection is most often used when the long axis of a state or zone is in the east-west direction. For example, Virginia and North Carolina. The UTM, or Universal Transverse Mercator coordinate system, is another standard coordinate distinct from the state plane system. The UTM is a global coordinate system based on the transverse Mercator projection. It is widely used in the United States and other parts of North America, and is also used in many other countries. The UTM coordinate system is common for data and study areas spanning large regions. For example, several state plane zones. Many data from U.S. federal government sources are in a UTM coordinate system because many agencies manage large areas. Many state government agencies in the United States also distribute data in UTM coordinate systems because the entire state fits predominantly or entirely into one UTM zone. As noted before, all data for an analysis area must be in the same coordinate system if they are going to be analyzed together. If not, the data will not co-occur as they should. National coordinate systems. Many governments have adopted a standard project for nationwide data, particularly small and mid-sized countries where distortion is limited across the spanned distances. Conversion among coordinate systems. Conversion from one projected coordinate system to another requires using the inverse or forward projection equations passing through the geographic coordinate set. So, for example, given a coordinate pair in the state plane system, you may calculate the corresponding geographic coordinates. For example, it might have come from NAD 83, as we see in figure A over on the right side of the slide. So first we convert from our map projection into our geographic coordinates. Then you may apply a formula that converts the geographic coordinates to a UTM coordinate system. And that way we get coordinates for a specific zone using another set of equations so that we get the UTM. A data transformation is often required when performing map projections. And we see this in illustration B on the right of the slide. Datum transformations account for differences in geographic coordinates due to a change in the shape or origin of the spheroid, and in some cases to datum adjustments. Datum transformation should be applied as a step in the map projection when the input and output datums differ. So here we go from UTM to geographic coordinates in NAD 83, then from geographic coordinates in NAD 83 to geographic coordinates in NAD 27, and then we convert the NAD 27 to an Iowa state plane coordinate system. Care must be taken when converting among projections that use different datums. If appropriate, we must insert a datum transformation when converting from one projected coordinate system to another. A datum transformation, described earlier in this lecture, is a calculation of the change in geographic coordinates when moving from one datum to another. Users of GIS software should be careful when applying coordinate projection tools because the datum transformation may be omitted or an inappropriate datum manually and automatically selected. And that concludes our lecture for tonight.